spaceships circle the moon, men will peer into its craters. We'll get our first look at the dark side of the moon, and someday it will be as familiar as the side we see now. Spaceships will move in closer to the sun to study the source of all the Earth's energy. The first step into space was planned by the scientists conducting the International Geophysical Year. To carry out space studies, the scientific community called for an unmanned satellite in an orbit above the Earth during the IGY, an 18-month period of intense solar activity from July the 1st, 1957 to December 31st, 1958. To this call, two nations responded. One was Russia. The other nation to launch an Earth satellite program for the IGY was the United States. The American satellite program was made the responsibility of the Naval Research Laboratory. Research programs at NRL extend into many scientific fields. Among them are electronic miniaturization, missile tracking, radio communications, and radio astronomy. Named to direct Project Vanguard was a man with wide experience in radio astronomy, Dr. John P. Hagen of NRL. NRL and the Martin Company had worked together on Viking, a single-stage research rocket which had set important records for altitude and velocity. On September 23, 1955, the Office of Naval Research awarded Martin a contract to design and build the rocket for a far more complex mission. A veteran of the Viking program shoulders responsibility for all phases of Martin's effort. He must get the job done and must get it done during the IGY. This is a tight schedule for all the technical people on Vanguard, men like these assistant project engineers. They have ahead of them a difficult assignment, for the rocket must lift a satellite to injection altitude, point it in the correct direction, and impart to it the velocity to keep it in orbit. This engineer heads the group that designs the Vanguard rocket airframe, its many parts, small and large, and its ground support equipment. Aerodynamics and propulsion. These problems lie in this man's field. A specialist in structures must tackle the weight problem. He determines what materials are light enough yet strong enough for the job at hand. The guidance and controls engineer develops a guidance system to tell the rocket if it is following the correct flight path and a control system to carry out the commands of the guidance system. The engineer in charge of testing has a double responsibility. He first sets up the test program at the plant, then he moves on to Cape Canaveral and tackles the job of getting the rocket ready for launching. These are young men in a young science. To weld these men and their groups into an engineering team, this is the job of the project engineer, the man in charge of the technical phase of the rocket program. Studies move ahead on the orbit, the environment in which the satellite must live. The lifetime of an orbit depends on its perigee, the point where the satellite is closest to the Earth, where the friction from the atmosphere is greatest. This was the goal set by NRL in the contract, an elliptical orbit with a minimum perigee of 200 miles. To ensure this high perigee, the satellite should be injected into orbit at an altitude of 300 miles at a velocity of 25,000 feet per second.
25,000 feet a second. That's a lot of velocity, Don. 4 times as much as Viking. How many pounds of thrust did we have on Viking?
21,000 pounds.
And on Vanguard?
27,000 pounds for the first stage engine.
Well, that's not much for this mission, Don.
Enough. We can do the job with 27,000 pounds. Why use 50 or 100,000?
Well, because it's easier with 50 or 100,000.
Jack, let's not lose sight of the ground rules. On this project, we are to make use of the best engine available, as of now. It'll do the job, provided we come up with an efficient design.
All right, Don. I'll buy that. Learn to get the maximum energy out of your thrust, no matter what it is. Is that right? Then you're set, whenever the high-thrust engines become available.
We'll take the future when we come to it, Jack. We have an immediate problem. We have to put a satellite up in time to help the IGY people. There's 2.5 years to do the job. Now here's what we're going to do. With Viking, we had one of the highest mass ratios ever produced. That rocket was 80% fuel. With Vanguard, we're going for an even higher mass ratio.
if it carries a higher percentage of fuel than Viking, we'll be designing a fuel truck.
A fuel tank that can fly. This, in effect, is what we had to design. To produce the energy needed to orbit a satellite, we must build a rocket that is, by weight, at least 90% fuel. Even with the best fuels available, a single-stage rocket cannot give us all the energy we must have. But it can lift us past the densest part of the atmosphere and give us a vehicle already moving at a high velocity when a second stage takes over. But though the second stage can lift the vehicle to the injection altitude of 300 miles, it falls far short of the orbital velocity needed. For this, we must build a three-stage rocket. Add a nose cone to protect the satellite from aerodynamic heating, and the result is a Vanguard configuration. That is, if it holds up after the aerodynamics group studies it and tests it as a model in the wind tunnel. Only 20 inches long, but it is the first Vanguard model, ready for wind tunnel tests at the Army's Aberdeen Proving Ground the last week of October 1955. Wind tunnel data tell the engineer where the structure has to be extra strong, where it can be lightened with safety. Since the rocket by weight must be 90% fuel, the structures engineer has about 10% left for actual structure, and he must share this 10% with guidance, controls, instrumentation, engines, and with the satellite itself, a 21.5-pound ball. He must strike a delicate balance. He must find material strong enough for the hypersonic Vanguard mission, yet light enough to permit the highest percentage of fuel ever carried in a large rocket. The thrust of the first stage engine determines the rocket's weight. Unless the fueled rocket weighs a safe figure below 27,000 pounds, it will never get off the ground. The safe figure for Vanguard is 22,000 pounds. On Viking, the fins weighed 185 pounds. We saved weight right at the start with a decision not to use fins on Vanguard, for the Viking program convinced us that the gimbaled engines made fins unnecessary, even though no large rocket had ever been flown without fins to stabilize its flight. We save weight, but we make the job of the controls engineer more exacting. With fins, Viking is a stable rocket, just as an arrow with feathers is a stable arrow. Vanguard, without fins, is theoretically unstable, like an arrow without feathers. But Vanguard's flight must not be wobbly. Its controls must keep its flight stable on the way to the target. But target for Vanguard is not a bullseye, but rather an altitude, attitude, and velocity that we can hit only by following a flight path worked out in detail in advance. This trajectory is different from that of Viking, but from Viking's journey straight upward, we learned the basic principles. We learned to control a rocket in pitch and yaw by directing its thrust vector, and in roll by roll jets. The means of sensing any deviation from the flight path is the gyroscope, but one gyro won't do the job. We must have one for pitch, one for yaw, and one for roll, each spinning in a prearranged reference to the rocket. If the rocket goes off course, its reference to the gyros changes, and they in turn send this information to the electronic brains of the rocket, the autopilot, housed in the top of the second stage. The autopilot's job? To evaluate the message of the gyros and to translate it into commands for correction, sent out to roll jets and to the actuators which control the direction of the rocket's thrust. Here is a rocket engine designed to Martin specifications. The propulsion engineer must work always with chemicals in which are locked explosive reserves of energy. In the first stage engine, we work with simple familiar chemicals. For the fuel pump, concentrated hydrogen peroxide. For the oxidizer, liquid oxygen. And for the fuel, kerosene. A refined version of the common household coal oil, the kind an earlier generation bought at the general store, but at the same time, the best fuel available for this type of engine. In the second stage, there is nothing simple or ordinary about the propellant. White inhibited fuming nitric acid is the oxidizer. The fuel is unsymmetrical dimethylhydrazine, a chemical as complex as its name. For the second stage, this combination is made to order. The second stage engine must fire from high in the air, where failure to ignite leaves us with no second chance. So for the oxidizer fuel combination, we use two chemicals that permit no misfire because they ignite on contact. In the third stage, we turn from liquid fuels to a solid propellant rocket, similar in many ways to those which boost missiles into the air. In the early days of the contract, work moves forward on many levels: aerodynamics, propulsion, structures, controls, design, all in a constantly changing give and take kind of interdependence, all working toward the day when ideas on paper become hardware for testing. And when that day comes, test facilities under construction will have to be ready. We build a structural test tower and a blockhouse from which we conduct pressurization and controls tests. We build a tower for the final vertical checkouts before shipping the rocket to Florida for launching from Cape Canaveral. This bolt has a big job to do for Vanguard. Explosive bolts separate the first stage from the rest of the rocket. Once its propellant is exhausted, the first stage is dead weight, a luxury this exacting program cannot afford. Important as weight saving is, just as important is the way we save this weight. Unless we get a good clean separation, Vanguard will be knocked off course. For a clean job, all 6 explosive bolts must fire at the same instant.
Fire!
With the second stage, the separation procedure is different and even more critical. The second stage houses the guidance and controls package. If the third stage is knocked off course during separation, no further corrections can be made. With a clean separation, the third stage can continue on the correct flight path, but to stabilize it in flight, it must be spun like a rifle bullet. Here is the sequence. When the rocket coasts up to peak altitude, the coasting time computer sends the fire command to 2 tiny rocket motors which spin the turntable. Then retro rockets fire in reverse and slow down the second stage. At this point, the third stage spins right out the top of the second stage and is ignited for its final thrust. The wobble here is a predicted test condition and will not be a factor in actual flight firings. In Florida, too, testing goes on for Project Vanguard at the Air Force Missile Test Center. From Cape Canaveral, the Air Force, the Army, and the Navy fire missiles and rockets out over downrange tracking stations stretching 5,000 miles into the South Atlantic. The field crew makes ready to launch Viking number 13, designated TV0 in the Vanguard test program. The purpose of the test, chiefly, to evaluate NRL tracking and telemetering equipment to be used later in the program. Preparations start in daylight for a launch set to go on the night of December 7th, 1956.
Five, four, three, two, one.
When the returns are in, the launch is a success. Tracking and telemetry both check out in satisfactory fashion. The altitude, 110 miles, impact point, 170 miles downrange at the designated point near the Grand Bahama Island. In January of 1957, with the start of the International Geophysical Year only 6 months away, the weight situation was under control. Less than 4% of the total weight was structure, an even better mass ratio than Viking. By using magnesium alloy where possible instead of aluminum alloy, we saved 39 pounds in the first stage and 14 in the second. We had a rocket that was light and strong. There is a difficult assignment ahead for the first stage engine designed by General Electric and static tested at Malta Test Station in upstate New York. This engine must lift an 11-ton vehicle off the launch pad and propel it some 36 miles upward. At Burnout, the vehicle should be traveling at least 5,500 feet per second. To do its job, this engine must burn for close to 150 seconds, twice as long as the old V2 rockets. From tanks above the engine, fuel is pumped into the thrust chamber, which will encounter some of the conditions it will face in flight. Fuel flow, mixture, pressure, and temperature. These are all things that must be checked out from within the blockhouse.
The igniter is armed, standing by for the LOX crash. Here's the crash, here comes the count. Coming up on X minus 35 seconds. X minus 35 seconds, mark. Coming up on X minus 30 seconds. X minus 30 seconds, mark. Secondary emergency water is on. Coming up on X minus 25 seconds, mark. Emergency shutdown power check. Coming up on X minus 20 seconds, mark. LOX vent is closed. Pressurizing LOX tank. X minus 15 seconds, mark. 14, 13, 12, 11, 10. Gas purge is on. 8, 7, 6, 5, 4, 3, 2, 1, fire. Igniter's burning. First fire. Main stage. +1, +2, +3, +4, +5, +6, +7, +8, +9, +10. +15, +20, +25, +30, +35, +40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, all off.
The second stage engine and tanks are built by the Aerojet General Corporation at Azusa, California. The tanks contain white inhibited fuming nitric acid and unsymmetrical dimethylhydrazine. This engine will take over after the vehicle is about 36 miles up. It must produce 7,500 pounds of thrust and burn for approximately 120 seconds. It must carry Vanguard to peak altitude and at the same time increase the rocket's velocity to 13,000 feet per second. Test areas for rocket power plants must be isolated spots. At Redlands, California, the Grand Central Rocket Company builds and tests a solid propellant rocket which comprises the entire third stage. This stage is small compared to the other two, only 5 feet long, less than 1/10 the length of the overall rocket. Since it must spin in flight, the third stage motor is rotated at flight speed to test it for balance.
9.
The flag goes up.
11, 12, 13, 14, 15.
Data reduction tells whether or not the third stage engine is ready to be shipped to Florida. There it will be placed on top of Viking number 14 and fired as part of an actual launch. The combination will become TV1, a rocket to test Vanguard's third stage propulsion unit under flight conditions.
9, 8, 7, 6, 5, 4, 3, 2, 1. A tape recording brought back from the blockhouse draws groups of engineers
who listen in on the launch of TV1 and the successful separation 120 miles up.
Plus 40 seconds. Plus 245, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. Plus 265. Plus 270.
They have reason to be pleased. Data on third stage performance was so complete that NRL permitted a change in the test program. Instrumentation could be taken out of the nose cone, and in its place could be substituted a small test satellite. More tests crowd a busy program. Pressurization systems must be checked out, and to keep on schedule, testing goes on by day and by night. Control testing continues. Pitch and yaw jets must be checked out thoroughly. After second stage burnout, when the rocket is in the critical coasting flight phase, these jets will control the vehicle in pitch and yaw. We tip the test rig to simulate the vehicle veering off course, and then we see if the jets can return it to the flight path and stabilize it. First stage roll jets keep the heavily loaded rocket from rotating in flight. For this test, we work with the same chemical the field crews will use later, and with a chemical as corrosive as concentrated hydrogen peroxide, we take the same safety precautions. The principle of the roll jets is a simple one. If the rocket starts to roll in one direction, from a roll jet in the opposite direction, we exhaust high-temperature steam from decomposing hydrogen peroxide. When these forces are in balance again, the roll is arrested. The test is completed. To save still more weight, the nose cone must be discarded as soon as its work is done. The two halves of the cone are held together by an explosive bolt housed in a fitting which acts as a blast shield and contains a coil spring. The small satellite for the test launches and the larger satellites to be used later, both of these are protected from aerodynamic heating by the nose cone. The tip of the nose cone is solid titanium, the rest phenolic asbestos, molded at low pressure to keep the volatiles in the phenolic from blistering the skin. Between 44 and 60 miles up, the nose of the rocket will encounter the highest temperature any external part of the rocket will have to withstand, 2,750 degrees Fahrenheit. But past 60 miles, the atmosphere thins out. Aerodynamic heating ceases to be a problem. The antennas and the delicate instrumentation of the satellite no longer need a protecting cone. Separation must be clean so that antennas are not damaged, and it must be quick so that the cone halves clear the onrushing rocket.
3, 2, 1, launch!
Scientists at NRL also face a weight problem in designing a satellite that can weigh no more than 21.5 pounds. All electronic equipment in the satellite is sub-miniaturized. The radio transmitter weighs only 13 ounces, yet it must send back a signal that tracking stations can follow as the satellite orbits around the Earth. There will be several types of satellites equipped with instrumentation for many scientific investigations. They will study atmospheric density, temperature and pressure at high altitudes, cosmic ray intensity, the total magnetic field, the changing patterns of the clouds over the Earth. The Lyman Alpha satellite can study the effect of solar activity on radio communications. A large solar flare erupts with the power of 1,000,000 H-bombs. Its flash spreads over hundreds of millions of square miles. Simultaneously, on the Earth, 93 million miles away, shortwave reception fades out sometimes for hours. To gather data on how solar activity can disrupt radio communications so promptly is the job of the Lyman Alpha satellite.
program to bring you a special bulletin from the Associated Press. London. The Moscow radio said tonight that Russia had launched an Earth satellite. The broadcast was heard in London. The announcement was made in an English language broadcast. We return you now to the scheduled program. As developments occur, we will pass on to you the latest news bulletin.
The effect in this country is immediate. Families gather in their backyards to watch the skies at twilight and at sunrise. And for Vanguard, the pressure begins to mount. Next on the schedule is TV2, set to go on a cloudy, overcast October day. This is the full Vanguard configuration, but the internal components are not complete. There is no satellite, and the second and third stages are dummies. This is a limited area test to check out the rocket's aerodynamic characteristics and the performance of the first stage propulsion system. A successful flight, the third in the Vanguard program, 3 for 3, but not one of the 3 tests combined enough of the functions of the full 3-stage rocket to permit even an attempt at putting a satellite into space. Dawn, December 4th, 1957. This is the time set to fire TV3, the first full-dress Vanguard, complete with 3¼ pound satellite. But the winds blew hard, 20 miles an hour, a little higher than the 17-mile-an-hour limit. The rocket moves slowly as it first lifts off the ground, a dangerous interval if a sudden wind hits. Still the crew worked, hoping for a break in the weather. But there are other troubles, particularly a leak in the liquid oxygen disconnect valve. With a temperature of 270 degrees below zero, liquid oxygen is treacherous to handle.
Test 1988 holding at T-minus 50 minutes has been scrubbed. Repeat, test 1988 has been scrubbed.
7.
The next try comes the 6th of December.
4, 3, 2, 1.
Fire.
Mark.
Flight analysis studies pinpoint the cause of failure: insufficient pressure in the first stage fuel system. On January 22nd, Vanguard is scheduled to try again, but a multitude of technical problems combine with the weather to block the launch of TV3 backup. After the gray clouds and rain, the brilliant Florida sun shone again on Cape Canaveral, and it shone too on America's hopes for sending up a satellite to join Sputnik. On January 31st, the Army's Jupiter C took off from the Cape, and we had our satellite. The first order of business, congratulations to the Army. The night of February the 5th, TV3 backup makes another try.
3, 2, 1.
Fire.
Mark.
At 20,000 feet, the control system fails and the rocket tumbles and breaks apart. Launch date for TV4, St. Patrick's Day. Maybe that's all we need, a little Irish luck. TV4 is scheduled to go at 7 a.m., reason enough to be in early that Monday morning to await word from the Cape. At a time like this, what are the thoughts of an engineer who's worked on this project right from the start? Does he remember how he studied instrumentation data to try to find why TV3 backup went out of control? Or does he think back to TV3? Does he remember the tests that worked perfectly, only to be reminded of all the things that must work perfectly for a successful flight? Or does he remember the nose cone separation test that didn't work and realize again that any flight can fail from a faulty wire, a leaky valve, or an explosive bolt that fires too late or too soon? At a time like this, what does an engineer think of?
He thinks the design of this rocket is sound. He knows it's been designed to do its job more efficiently, more economically than any other rocket ever built. He knows we learned a great deal from the two failures. We've increased the fuel pressure. We've beefed up the controls can area. We've utilized parallel wiring from the controls to the actuators. But until the first satellite is up, he worries.
At the Cape, the rocket countdown moves along without delay. 25 pages long, the countdown spells out each step in the Vanguard launch, spells out when a task must be started, when it must be completed. With TV4, it is, in effect, two countdowns. The first is 7 hours of servicing and checkouts the day before launch. Then, after an 8-hour rest period, the crew goes back into action for the final 6 hours. Weather checks occur throughout the countdown. These are the responsibility of the Air Force Missile Test Center. The range must also maintain close coordination between central control and tracking stations on the downrange islands. At T-minus 70 minutes, all major fueling is complete. The crew gets ready for the gantry to pull back from the rocket. Another weather check. The wind, satisfactory. The range intensifies its warnings to any boats that may be in the danger area, either near the Cape or one of the impact areas downrange.
Number 438. Time is running T-minus 35 minutes.
This is the danger period. The igniter is being armed. And the last man to leave the rocket heads for the blockhouse. From this point on, all aspects of the firing must be conducted from within the blockhouse.
Minus 14 minutes. Minus 140.
This is the time for roadblocks at all telemetry ground stations and for silence in the blockhouse.
On my mark, the time will be T-minus 120 seconds. March, minus 120 seconds.
Telemetering is ready. Radar stations are set for the launch. Optical tracking is ready.
Minus 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Fire! Mark. Plus 20 seconds.
What?
Plus 25 seconds. Plus 30 seconds. Plus 35 seconds. Plus 40 seconds.
Keep it quiet, please.
Plus 45 seconds. Plus 50 seconds. Plus 55 seconds.
As the rocket climbs farther and farther away from the earthbound tracking instruments, let us look at Vanguard now from an imaginary spot out in space. The TV4 first stage engine burns for 145 seconds. It lifts the vehicle to 41 miles and to a velocity of 5,836 feet per second at burnout. At 172 seconds, as planned in the rocket's program, the nose cone pops off. The satellite's transmitter, exposed to light and air, starts sending its signal back. Altitude, 74 miles. TV4's second stage delivers its thrust for 122 seconds. At burnout, the rocket is 175 miles up, traveling at 12,675 feet per second. Vanguard coasts up to peak altitude, and then, 405 miles up, the third stage is ignited. The satellite is sprung clear. Now comes a period of waiting. Up to this moment, Vanguard is a rocket that has done its job. Instrumentation tells us it has produced the velocity for an orbit. Instrumentation has not told us if it has produced the direction for an orbit. At NRL, the Vanguard Control Center awaits word from the tracking center at San Diego. "134 minutes. This was the time it took for Vanguard's first trip around the Earth. The satellite's highest speed, 26,080 feet per second. Its apogee, 2,462 miles out in space. Its perigee, 405 miles above the Earth. Its life expectancy, 200 years. The first Vanguard satellite will be orbiting the Earth when the space age it helped foretell becomes reality.